Hi everyone, welcome back to Econ 313. In this recording, we will be looking at Chapter 33, Making Risky Decisions. Okay. In this chapter, we will analyze decisions that involve a small probability of death, such as skiing or driving a car. Okay. So what we're going to do is first, we're going to define what is a risky decision. And then we will go ahead to try value life and death as well as pain and suffering. Okay. And lastly, we'll try to create a probability measure that is handy and convenient when we look at small probabilities. Okay. So that is just an outline of the topics in this recording. Okay, first, let's look at what is a risky decision. Okay, I want to differentiate this definition between the econ definition and the decision analysis definition. The latter is what we are looking at in this class. Okay, in economics, when we talk about risky decision, we're referring to decisions that are in an uncertain situation and where you may not know exactly how the world is going to turn out to be, but you do know the probability that the world around you will end up in. For example, the previous situation about weather. For Kim, in Kim's party problem, that is a risky decision in the economic sense. Okay, there are unknowns and you have some beliefs about the unknown weather. Okay. However, in decision analysis, which is what we're talking about in this class, we're defining risky decision more like the popular culture concept. So when we think about a risky decision in the decision analysis field, it is referring to a decision situation where at least one alternative or one option has at least one risk. Okay. And then we still need to define what is risk, right? And here, risk refers to such a prospect that has both a small probability of occurring and the promise of a large loss if it does occur. Okay. So here, I want to emphasize that a prospect needs to have both elements here, and here in order for it to constitute a risk. Okay, and then a decision situation that involves at least one risk is constituted as a decision, a risky decision. Okay, so if you have a decision situation where a prospect has a small probability of occurring, but when that prospect occurs, it doesn't incur a large loss. It doesn't incur a large loss. Rather, suppose it incurs a large gain, then it doesn't constitute as a risk. For example, if you are facing a certain decision situation where in one prospect you would inherit a large amount of fortune from some unknown distant relative, despite of that has a small probability it doesn't involve a loss. That prospect doesn't constitute a risk. Okay, so this is how we define a risky situation in this class. Next, we're going to look at how we can value pain, sickness. Before we go into the specifics, I want to issue a warning here that in the following materials, we will be discussing unpleasant hypotheticals such as sickness, death, and pain. Well, there are hypotheticals, but I just want you guys to put yourself in a certain scenario and try your best to imagine while we talk things along. Okay. Here, let's start with imagining that you're facing a painful dilemma. Okay. Through this imaginary story, let's see how we can value something intangible like pain. Okay. Suppose you go to see the doctor and you have received a string of bad news and good news. The bad news is that you're diagnosed with a fatal disease, which will kill you painlessly in a month. Okay. The good news is there is a treatment to cure this disease. However, again, the bad news is that this treatment is very painful. Okay, you need to stay in the hospital for 24 hours to receive this treatment, and you will experience continuous pain during the 24 hours. But the good news is you will live for sure after the 24 hours of painful treatment. Another good news is this treatment is covered by insurance, so you can think of this treatment as free to you. Okay. Now assume that you prefer this treatment, this painful treatment, to dying painlessly in a month. Okay. So now we're assuming that you would rather receive this 24-hour continuous painful treatment than being dead in a month painlessly. Okay, so this option is out. You do not want to go without the pain, but die in a month. Okay. Now this is the first thing I want you to imagine. And then the doctor goes on to offer you another good news. Okay, so you do have a second option in terms of treatment. Okay, in addition to the 24-hour endless pain, but definitely surviving, there is this second treatment option that involves an experimental procedure. This experimental procedure is good in terms of it doesn't incur any pain at all. You just spend also 24 hours in the hospital, but maybe just watching TV or sleeping, whichever you prefer. And still, the good thing about this second treatment is that you will live for sure after the procedure. It is very effective, this experimental procedure. Here's the catch. The experimental procedure is not free. It's not covered by insurance at all, and it is rather expensive. You have to pay for everything that is used to treat you in the 24 hours by yourself. Okay, here I want you to think about the first and second treatment and think about what is the highest price that you're willing to pay to get this experimental procedure rather than the first treatment. Okay, here I want to emphasize that we're comparing this second treatment with the first treatment because no matter which one you choose, they're all better than dying painlessly. Here, what we're looking for, or what I'm asking you to think about, is the highest price that you're willing to pay. Okay, as you can see, we have a definition whenever we talk about the highest price that you're willing to pay for something. It's called the willingness to pay. Okay, and when you pay the highest price, you would be indifferent between receiving the first treatment versus receiving this second treatment and paying that willingness to pay price that you have in your mind. Okay, at this point, you can sort of grab a piece of paper and write that price down on the piece of paper, and we'll come back to that later. Okay. Well, as it turns out, there is a third option in terms of treatment. that the doctor has to offer to you. Okay, this third treatment involves another drug. The good thing about this drug is it's still no pain. It is still painless. You still spend 24 hours in the hospital receiving the treatment. And another good thing is it is free to you. Okay, so insurance would cover it. You need to pay $0 to receive this third treatment. However, here's the catch. Despite the treatment having no pain and free to you, it is less effective. You may die painlessly at the end of 24 hours. Okay, so if you opt to receive the third treatment, okay, no pain whatsoever, even if there's a chance that you will die at the end of 24 hours. However, even if you die at the end of 24 hours, it will still be painless. There still will not be any pain that comes with it. Okay. And here's something I want you to think about. What is the highest probability that you're willing to take to go with this drug instead of the first treatment? Okay. Again, we're comparing this third treatment with the first treatment. Okay. And we're trying to think about a probability that you for the event that you may die at the end of 24 hours, which will make you indifferent between receiving this third option and the first treatment. Okay. And again, the highest probability, at the highest probability of dying, you will be indifferent between this third treatment and the first treatment. Okay. So now you can write down this probability that you have on the piece of paper, and then we'll again come back to that. Okay. So as you can imagine, we are trying to establish some equivalence relationships between the first, second, and third treatments. Okay, here's a summary. For the first treatment, you will incur a lot 24 hours of pain. So here, treatment 1 has a lot of pain, but you will survive for sure. However, but also it is free to you. Now, in thinking about the second treatment, you are avoiding pain and you're still going to be alive for sure, be cured of the disease. However, there is a cost, and the highest price that you're willing to pay for treatment 2 is the dollar amount that you have written down on the piece of paper. Let's say, let's call it $X, because each one of you may have a different X amount. Okay, it can be $100, it can be $1,000, it can be $10,000. So this is your personal willingness to pay to get treatment 2. If you think about this X dollar is your personal willingness to pay to avoid the 24 hours of pain if you were to receive treatment 1, right? So that is the X dollars. What is it for? Okay. And then in treatment 3, you still get to avoid the pain. You avoid the pain not through paying some kind of cost, but through accepting a possibility of death. Okay, so the highest probability that you have just written down is P over here. You are willing to avoid pain by accepting a probability of death that is equal to P. Okay. Suppose you are offered a treatment 3, with a probability of death that is below your highest probability, P, then you would opt for treatment 3. If you're offered a treatment 3 with a probability of death higher than the P that you've written down, then you would opt for other treatments rather than treatment 3. Okay, so that is how you think about the P and the x that you have written down. Okay, given this information, you can pause this recording and reflect again what is the x dollar and what is the p that you really are willing to take. Okay. Here, this pain-free but life for sure describes this treatment. This describes this treatment. No pain, pays $X, pays some kind of dollar, but live for sure. And here, you don't have any pain, it is free, but you die with probability P. And as you can imagine, this tilde sign represents equivalence relationship. Okay. So like I said, these two treatments, treatment 2 and 3, are essentially two ways to avoid the pain in the first treatment option. You either pay X dollars or you pay by accepting a probability of death. Okay? Since you're indifferent between treatment 1 and treatment 2, you're indifferent between treatment 1 and treatment 3, then you are indifferent between receiving treatment 2 and 3 by, relationship of transition. Okay, since they are both equivalent to the first treatment, then they must be equivalent to each other also. So now we can calculate sort of an exchange rate by dividing X dollars with P. Okay, what does that mean? That is essentially the dollar amount that you're willing to pay to avoid a 1% probability of death, right? So you're paying X dollars to avoid a probability of death that is equal to P, because if you look at these two, there are no pain, so these two are equivalent. One involves a probability P of death, one involves paying X dollars. Okay, and these two should be equivalent. Then X over P is the dollar amount that you are willing to pay to reduce the probability of death by 1%. Okay, so this X over P is actually your willingness to pay to avoid probability of death. Okay, and that X dollar itself is your value or your willingness to pay to avoid 24 hours of pain. Okay. This number, X over P, could be very large and hard to interpret, okay? Because, if you're like me, I would not even to accept a probability P equal to 1% here. It might be 0.00001. Okay, here's an example that may work for me. So my $X is $10,000, and my probability P is equal to 0.001. Okay, if we do the math of dividing X with P, it would be equal to, what is it, $10 million, right? $10 million is the dollar amount that I associate with 1% of probability of death. Okay, so this is a very large number, and of course we want to represent it using a sort of easier number, or not easier number, but a shorter number, and fortunately there is a way to do that. Okay, so what we're going to talk next is to how can we come up with a measure to represent smaller probabilities and then represent this X over P. Okay, so when we talk about small probabilities, it is very often in the medical, whenever you're talking about medicals, you may need to talk probabilities in very small scales. For example, in medical informed consent, if you read some risk is too small to worry about, we're talking about below 1%. Okay. However, even if it is below 1%, even if it is a small probability, if the consequences are serious, like life or death, we sometimes care about them. For example, if you're thinking about using seatbelts or helmets, the probability of having a car crash is very low. However, if it does happen, then you will incur serious injuries or even death. Like I said, whenever we're discussing these probabilities, for example, 1 over 10, 1 over 100, 1 over 1,000, it is pretty cumbersome to discuss it. So what we can do is to define a new unit of measuring probability so that we don't need all those zeros. So what we can come up with is another unit of measuring probability, which is called microprobability. We use this symbol to represent it. Mu, p, represent such a probability unit that is equal to 1 over a million. Okay? Just to give you sort of some perspective. What is the probability? What is the event that you will see in the real world that has a probability, that has a micro probability of 1? Okay, so here if you toss a fair coin 10 times, the probability that all the 10 times that you toss the coin land in head is about 1,000 μp, 1,000 micro probability. Okay. If you do that, if you toss the fair coin 20 times, the probability that all 20 times it land on head is about exactly 1 micro probability. Okay. As you can imagine, if you talk about the second scenario in probabilities rather than in terms of micro probabilities, you would say 20 heads in 20 tosses is about 1 over a million probability, which is very hard to read with all these zeros. You could just say it is 1 micro probability. Okay. It is just like when we talk about units to measure length. Sometimes we use meters, sometimes we use inches, sometimes we use millimeters. Okay, so this is more like the millimeter equivalent in terms of measuring length. Okay, here let's formally define microprobability, and we use this. This symbol is called mu p. We use this to represent the chance that is equal to 1 over a million chance. Here's a new definition. Micromort is a microprobability of death. Okay, so it is the same essentially as the microprobability. However, when that microprobability is measuring the event of death, we call that micromort. Okay, and we have a new symbol for it, mu mt. Okay, so 1 mu mt is essentially describing 1 over a million chance of dying. Okay, rather than just 1 over a million chance, it is 1 over a million chance of dying. Versus mu p is only referring to the 1 over a million chance. Okay. So now we can come back to our exchange rate between the dollar amount and the probability. Okay. Instead of doing x over p as we did in the previous slide, we can do x over a million p, which is essentially x over mu p. Okay, and this is called the micromort value. It is the exchange rate in dollars per micromort. So this is the dollar amount that you're willing to pay to reduce the probability of death by 1 micromort, which is by 1 over a million chance. Okay. For example, over here, when we talk about p is equal to 0.001, it is equal to 1,000 micromort. And then you divide x with this new p, then you will have $10 per micromort, which represents the fact that you are willing to pay $10 to reduce the probability of dying by 1 over a million chance, rather than by 1% chance. Okay. And as you can imagine, whenever the micromort is even too large to measure the probability, we can also define nanomort, which is 1 over a billion chance of death. Okay, so now we have talked about how to value death, how to value pain, and how to represent probabilities in very small scales, especially how to represent probabilities that are associated with dying. Okay, now you can think for yourself about some risky activities you're thinking about trying. Again, remember, risky activities refers to such activities that may incur a very large loss with a very small probabilities. And you can think about the situation, well, specifically the decision about whether to go for the risky activities or not, by thinking first about the chance of death in that activity, and think about what microprobability of death makes you indifferent between participating in the activity or not. Okay, there are a couple of examples that you can find in the textbook thinking about evaluating risky activities. Okay, here's one example of using micromort values to decide whether you should go on a ski trip or not. Okay, what you should be thinking as someone majoring or minoring in economics is that you should do a cost-benefit analysis in terms of deciding whether to go on this ski trip or not. Okay, and like I mentioned before, as economists, we like to, attach a dollar amount to everything. So when you think about benefits, you can think about all the fun that you're going to have, and then what you want to do is to attach a dollar value to those fun. Okay, and now add those up, you will have a total benefit of going on this trip. However, on the other side, you will definitely have a lot of costs. First of all, you need to pay for the ski trip and everything, so you will have a dollar out of pocket cost in terms of arranging this trip. Then you will spend a lot of time hassling in the and have a lot of hassle in terms of waiting in lines and the pain of traveling. Lastly, do not forget about the risk of injury and death. Okay, so when you think about risk of injury or death, you can tap into the micromort value that you had figured out before using the imaginary example. For example, in the previous exercise, you have established that your micromort value is $10 per micromort. Okay, so every 1 in million chance of death incurs a cost of that is equivalent to $10 to you. Now, what is the risk of skiing? Okay, so here are some. You will find a lot of figures in Figure 33.2 in the text, but specifically for skiing, if you're going to Breckenridge, Colorado, it is 1.5 micromort per day, and you're going on a 3-day skiing trip. That is 4.5 micromort for the entire trip. Then each micromort is costing you $10. Then the whole trip is costing you 4.5 times $10, which is $45. So this is the cost of risk of death. It's not the cost of death, it's the cost of the risk that you are facing in terms of death if you do go on the ski trip. That is this item here. The dollar value of the risk of injury and death. Injury is something you need to figure out for yourself, but the risk of death is valued at $45. So when you do the cost-benefit analysis, make sure that you add that $45 to the cost side. Okay. And in terms of risks, here are some common risks that people face in US. And if you can think of, if you look at all these causes and then look at the odds, and then the odds represented as a micromort. And here mu-MT, recall that this specifically refers to the microprobability of death. Okay, so cancer has 2,500, and then drowning has 15 micromort, which is 1.5 in 100,000 odds, and then floods and the hurricane. Okay, you can definitely read chapter 33 if you want to explore a little bit more on this aspect. And in chapter 34, the textbook talks about death in larger probabilities. Okay, both are interesting chapters to read. Okay, so this is the end of this video.